let's begin. So circular motion. So we looked at the simulation a while ago about this blue circular object moving around a common center of mass. Right, what we're looking at here now, I'm gonna just give us diagram so we can use that to make sense. Alright, hold on, give me a second. Let me just fix this so I can create a circle out of it. Alright, so here we have a circle, right? So let's say that this is the path of a moving object, right? Let's say that the object here, object A, is traveling on this line. Alright, so object A. Let me not call it object A because I want to use A for stuff. You know what? Let's call it object A, it's fine. Alrighty? So object A is moving along this path, right? With some velocity. We're gonna describe the velocity first, right? But well, at a time. But give me a moment, right? So let's look at the center of the circle. It's going around a center of mass, right? At a specific radius away. So there's a distance away from the center that we're looking at. Just want to describe this structure and then we get into the physical quantities, right? And it's moving along this circle already. So we're looking at that. We should actually have a velocity as well. So it's moving at a constant velocity. Velocity would be tangential to the circle here. Hold on, let me just perfect this. So the velocity here would be tangential. So the velocity v, right? And the path would just be the arc of the circle, right? So let's say that A moved from this initial position, right, and moved up here to this other position up here, right? This part of the circle, the part of the circle here that it moved, that would be our angular displacement. So that would be the distance in which it moved in a particular direction, in the circular direction, right? So that there would be our angular displacement. Right, so it's same thing like if a man were to move from A to B, that would be a displacement, right? What we're looking at here from the initial position to the final position along the arc of a circle, that would just still be the displacement. But because it's about an angle, right, we call it the angular displacement. All right, so let's just describe this here. So this displacement is about an angle theta. So that's why we call it an angular displacement. All right. I'm going to formally be writing down the definitions as we go along, but I want us to see what's happening here first. Alrighty? So we're just looking at that first. Is everybody good so far?
Yes.
Alright. So so that is generally what we're looking at first of all, right? So an object is moving along a circular path, right, with a tangential velocity, meaning that when it's moving, right, the velocity will always be a vector that is at a tangent to the circle, right? And it's always moving with respect to the center of mass, right? So the an object in center or where it's attached, right? So let's start getting some terms in, right, to understand really what's happening here. So there are key terms that we need to understand about circular motion. Hold on, let me just rearrange this here. Perfect, right? So we need to know these general key terms here. So we need to know angular displacement, right? So we need to be aware of angular displacement and what angular displacement really is, right? So that's the first term that we need to really understand to get under wraps, right? There's another term that we need to know. We need to know the term angular velocity. We also need to know, what else do we need to know? We need to know the centripetal acceleration. And we need to have an understanding of the centripetal force. All right. So we need to have an understanding of all these general criteria. Alrighty. So let's look at this. So back to our general diagram that we have here, right? So we have an object moving in a circular path at some velocity, and it continues to move around in that circular pattern. Now, at any point along that path, we should be able to discern how much force is acting on that object. So the centripetal force. So it's centripetal force just speaks to the force acting on an object that is moving in a circular pattern. Right? We must be able to describe its velocity, its acceleration, and its angular displacement in time. Alrighty? So before I go any further, are there any questions? Before I go any further, because we're going to go into a bit of math. Alright, so I'm not hearing any issues there. Alright, so as we discovered, or we spoke about the angular displacement already, right? So we have a circular path and a specific section of that path. If it were to move from here, an object were to move from here to here, right? That would be its angular displacement, the arc length, right? We can get its angular displacement from that length. Alrighty? The change in distance. So we can get the displacement from there, right? As it relates to the velocity on an object, right? So let's look at the velocity there. So that would be the angular displacement. For angular velocity, as I was stating here, if an object is moving along a circular path, the velocity would be tangential to the path itself, right? So the velocity will be moving in that direction. Right, so if we were to have the object up here, let me just put the object at four different areas, right? The velocity while it's at the top of the circle here, right, would be tangential. The velocity here also would be tangential, and the velocity here. All right, so everybody understands this thing.
Yes, sir.
All right. So we're just speaking about the tangential nature of the velocity, right? So if it's moving to the west, to the east, to the north, to the south, right, there will be a velocity acting on it, right? But because it's moving in a circular motion, the vector, the direction of velocity, will continue to change as it moves into that in that circular motion, right? Along with the velocity acting on it, or the angular velocity acting on the said object, right? There's a force that is dragging it to the center of the circle, right? So I want to use a different color to show that force, right? So there's a force keeping it in that circular path, right? Which is perpendicular to the velocity, right? That force F is what we call the centripetal force, right? So an object is moving along a curved path. So let me just make it simpler, right? So object is moving along a curved path here, right? With some tangential velocity that we will describe, right? And along that circular path, right, there's a force that is pulling it to the center, right, of the circular path, which is our centripetal force, right? So the change in distance on the circular path is what we call the angular displacement, and we're going to be describing each and every one of those factors, right? So without the thing is, no, it's maybe a little bit difficult to describe when I'm not in person, but hopefully, right, as we go along, we'll be able to describe them a little bit better as vectors. Alrighty, so that's generally what we're going to be looking at. So let's get to the meat of the matter, right? So our syllabus requires us to look at these four different terms, and I went through them a little bit. Centripetal acceleration is something that we will get an equation to calculate, right? So let's begin there. All right, so let's begin with the math here. Remember, if there are any questions, you guys can let me know so we can clear it up. All right. So let's start off with our angular displacement. So firstly, let me change that. So the first thing that we're looking at is our angular displacement. For our angular displacement, as we said, right, it is angular displacement is at an angle, right? It is the angle through which an object moves, right? So we're looking at that. So remember what we stated. If an object is moving along a curved path here, right, it is displaced from our initial area. Let me just use an X to show position to our final position here, right? So it moves along this area here, really and truly it moves along here, right? Remember, every circular motion is with respect to some center of mass or center of gravity, right? So there's an angle that is formed here. Alright, so let me just draw this back. So there's an angle that is formed here, right? So we're looking at how much is that displaced on in an angular way, right? So the angular displacement is the angle through which an object moves on a circular path, right? So do I need to write that down or is that fine? Let me just write it down. It's the angle through which an object, right, moves in a circular path. That's really and truly what it is. Right, so we're looking for that angle. So we need to also note that this angle is given in radians. Right? So if we were to look at it, right, this angle is denoted by theta, as we stated there, right? So theta is gonna be related to the arc length, right? So what is the length that we have here? So the length from here to here, that arc length is represented by S, right? So we have that there. And it's also related to the radius of the circular path, right? So everybody can understand what's happening here? Just a quick check-in. So it's fine so far. So an object is moving along a piece of circular path, right? We're going to try to find the angular displacement based off of the arc length of the circular path and the radius of the circle itself, of the path of the circle, right? Or the path of the object, all right? So the theta, right, is going to be in relation to the arc length. That is not arc. So to the arc length, right, which would be denoted by S divided by the radius R, right? So therefore, theta is equal to S over R, right? Where we know that theta is the angular displacement, right? S is the arc length, or distance traveled along the circle, and then R would be the radius of that circle. Alrighty? So remember that this is given in radians. So the unit is rads, radians, right? So the relationship between radians and degrees. So anybody knows the relationship between these? Not sure if you guys looked at it before. Alright. So let's get the relationship on the way then. Alright, so let's look at this, right? Say we just have a regular circle. Why is the circle not circling? Hold on. Oh, because it broke in the middle of it. Alright, so the circle is not circling. But let's say that we have a circle here, right? right? Let's divide these into quadrants specifically, right? So let's say that we're starting at 0 degrees here, right? So we're moving off from 0 degrees on the x-axis, right? We have the x-axis and the y-axis, right? So if we were to move, let's say in this direction, right? This would be what? A 45-degree angle, right? Following? Is everything fine so far? Okay, I'm not hearing you guys. I'm not hearing what you're saying properly. But I'm assuming that everything is fine so far, right? That would be 45 degrees, right? So we have that there, right? So we would describe any angle along the circle, right, with a degree, right? But looking at this, right, what we need to know, right, is that half a revolution, right, or 180 degrees along a circle, right, is equal to pi radians, right? Therefore, one full revolution, which is 360 degrees, right, that would be equal to 2 pi radians, right? Therefore, if we were supposed to draw angle 45 degrees, right? So let me just write it, 45 degrees. That would be equal to how many radians? That would be equal to pi over 4 radians, right? So it's just looking at the relationship between radians and degrees. So 180 degrees is pi radians. So 360 degrees are what we call a full revolution of the circle. That would be 2 pi radians. Alright? So how do we convert radians or convert degrees to radians? If we're looking at that, so how do we do that, right? So in order to get radians, let me use a, well, let's use whites. So in order to get radians, what we'll need to do is divide pi by 180 degrees, right? So we're doing this, and then we times it by the degree that we got. And in order to get degrees, right, we have 180 divided by pi times radians, right? So we just inverse to get those. Alrighty, is that fine? Alrighty. So we have something like that. It shouldn't be too bad. Alrighty, so it shouldn't be too bad. Hold on, let me see something. Let me just check something real quick to make sure that everything is fine. Alrighty then. So radians to degrees. So 180 right over pi should give us that already. So alrighty. So we're working on that. So one thing that you need to note as well, right, is that your calculator, right, needs to be in radians when you're working with these, right? So your calculator can be in radians, so you can give your angle displacement in radians, right? If you're working with something like that, right? If not, you can just work in degrees and then convert to radians. Hopefully everybody's familiar with their calculators, right, in order to get that. Alright, so everybody's fine so far? All right, so hopefully everybody's fine with that. Alrighty. So we're looking at the angular displacement there. So are there any questions or concerns before we move on? Any issues, any concerns? Alright, so everything there should be fine. Alrighty? Okay. Alrighty. So let's move on, right? So the next thing that we're looking at is angular velocity, right? So the angular displacement down. For the angular velocity now, right, we're going to look into linear velocity a little bit. Alright? So do you guys, well, we're working with that first, then we're gonna get into the examples. Right, so for our angular velocity and in circular motion now. So 2, the angular velocity. Alright, so hopefully we're following here. So the angular velocity, right, is denoted by omega. Right, let me fix that. So it's denoted by the symbol omega. Alrighty? Alright, so it is the rate of change of angular displacement. Right? So let's just write that the rate of change of our angular displacement. How did we get that, right? If we use linear velocity, right? Remember that linear velocity specifically is going to be the change in displacement with respect to time, right? As it relates to the angular velocity, this is linear. As it relates to angular now, the angular velocity omega would just be the change in the angular displacement over time. Is everybody okay with this? Alrighty? We can relate linear velocity to angular velocity, right? By using this equation. Let me just show. So this relation to linear velocity. If we look at the relationship between these two, right, we can state that the velocity, right, is going to be equal to the radius, right, times the angular velocity, right? So what are we talking about here? If we have the circle that we were speaking about, let's look at the circle. Right, we have a circle that we were speaking about. We know that an object moves along the circular path, right, at a specific tangential velocity, right, v. The angular velocity, so the velocity as we move around the circle, right, will be the displacement, right, not, well, the angular displacement with respect to time, right? But if we're trying to find the linear velocity at one point on the circle, right, that would be r times omega. Alrighty? Any issues or concerns? Checking the what's the meeting? Everybody's okay? Can we go over that? Okay, I'm just seeing the messages, right? Because I'm not really hearing. All right, so I'm not seeing the chat while we're going through this, so I need you guys to let me know what the issue is. So Josh said no a couple, a couple minutes back. Is everything okay there? I'm going to go over this, Divine, but what's happening here? I need you guys to speak to me. Oh, you're good. And Divine. Alright, so let's go over this then, right? So as we were stating here, right, we're giving these different things now. So the angular velocity, right, as we stated, right, would just be the change in the angular displacement over time, right? So same how we have regular velocity being displacement over time, angular velocity would just be the angular displacement over time, right? And the relation to regular velocity or linear velocity, right? This is the relationship here. So linear velocity, right, in centripetal motion or circular motion would be the radius, right, of the circular path times the angular displacement, right? So that's what we're looking at there. So when the object is moving around, if we're supposed to freeze the object right here, so that red dot is the object, right? There will be a tangential velocity, tangential linear velocity there, which would be r times omega, right? So the r times omega. The omega just looks a bit weird, right? But yeah, it would be r times omega, right? And then what we were talking about here, as it relates to the curved green arrow here, would be our angular velocity, which would just be the change in our angular displacement over the change in time, or over time, a period of time. Okay. Is anybody having issues with the notation that I'm using? Just check in. Let me go to the chat to make sure. Anybody having issues with that? I want to make sure that everybody's good. How is v, or how is the velocity equal to r times omega? So you want to know how that is possible. So you want me to derive that to show you? Alright, so let's show you. So you want me to show you this. Alright, give me a second. Alright, so let's look at how this came about. So what we're seeing here now is how. Alrighty? So let's start out first. We showed before, right, that the angular displacement, let me just cut this off, right? The angular displacement is equal to the arc length divided by the radius, right? If we rearrange the equation, right? So rearranging, right? We are going to get the arc length is going to be equal to the radius times our angular displacement, right? So we can note that, so we're starting from there, all right? So note now that our angular velocity, right, which is omega, is equal to our change in angular displacement over our change in time, right? And linear displacement, not linear displacement, but linear velocity is just a change in regular displacement over time, right? So we're noting all three of these things, okay? These are actually equal. So if we equate them, t is going to be equal to the derivative, right, or the change there, right? So we're gonna have the change in regular displacement. So we have linear velocity on one side, of angular, right? We're trying to get the angular on the other side, right? If we rearrange now, we can end up with v is gonna be equal to r d theta dt. And what is d theta dt? That is equal to omega. All right? Is that fine now? You can see where we got that? Okay. So we have that there. So that's how we proved that. Alrighty? So let's move on to the next line of concepts that we have to go through, right? So we've touched on the angular displacement, right, that we see here. I will look at the conversion to radians, and we need to note that angular displacement is in radians. We looked at the angular velocity, and we just proved the relationship between angular velocity and linear velocity, right? So now we're gonna have a look at our centripetal acceleration, right, and then our centripetal force. All right, so let's go. All right, so centripetal acceleration. When an object tends to move in a circular path, right, it is constantly changing direction, right? So remember what acceleration is. What is acceleration? Anybody? What's acceleration? I hope it's not too late for you guys, open your mics and talk, what's happening. What is acceleration? Anushka, Tonian, Christine, Josh. The rate of change of displacement. Alright? That is not true, but that's not too true. It's the rate of change of the velocity of an object, right? So it's a change in velocity with respect to some time, right? So it is, right? So we have that there. So remember, what is velocity now? What is velocity? Velocity is the speed of an object with some direction, yes? Velocity is the speed with some direction. So if we're moving in that direction at 30 meters per second, yes, that's velocity, right? The velocity would be 30 meters per second, right? Um, to the east, right? So that's velocity, right? So let's look at this now. If we are looking at a circular path, right, and an object is moving along a circular path, right, at different points, let's say at 0 seconds, the object is pointing in this way, going in that way. At 1 second, the object is going in that way. At 2 seconds, the object is going that way. And at 3 seconds, the object is now going that way. So we're changing the direction of the object as we move along the circular path. So if we change direction, doesn't that mean that we're changing the velocity? Doesn't it mean that we're changing the velocity as well? Because the velocity is speed with direction and we're changing the direction, right? That means that we're having some impact on the velocity, right? Even if the speed remains constant, we're having some change in direction. And that change in direction would require some acceleration, right? Or that affects the acceleration. So the object, yes, is accelerating along the circular path because we have change in velocity, which would result in a change in the acceleration. Does that make sense? Drop a 1 in the chat if that's okay. That makes sense, right? We change the velocity, we're ending up changing the acceleration of the object, right? So we have that there. So this change in direction requires some amount of inward acceleration. We'll call that the centripetal acceleration, denoted by A, right? So we're looking at the acceleration of the object towards the center. Acceleration A, centripetal acceleration. All right. So how do we get centripetal acceleration? So centripetal acceleration is related, right? So A, centripetal acceleration, is actually related to the angular velocity and the radius, right? By this equation. So it is related by this equation. Alternatively, if we look at its relation with linear velocity, acceleration would have been v squared over r, the radius, right? So this is our relationship between them now, right? So this is the acceleration. This is with respect to angular velocity, right? And this is in relation to linear velocity. So we have these, right? I'm trying to complete these topics so we can go into past paper questions after we're done, right? So I want to get the concepts underway, and then when we start doing questions, then we'll just go through them, restate the topics, and go through, all right? So this is the relationship between them, all right? So before we move on from this, is there, do we need to prove these? Does anybody require me to prove these? Let me just
Sure.
check. Oh, you said sure? All right, so let me just check. All right, so let me just prove them to make sure that everything is okay. All right, so let's prove these then. All right, so give me a second. Let me just let this person into the meeting. Prudent is here. So hello. All right, so firstly, right, we have two different forms, two different forms. They're kind of interesting, right? So let's start with angular velocity, right? So if we were supposed to start with angular velocity, so let's do this again. How? How so is that relationship possible, right? So let's start with angular velocity, omega. Omega is going to be equal to change in angular displacement over the change in time, right? So looking at that, right? The linear velocity is also, as we stated before, r times omega, right? The relationship between the two, the magnitude of centripetal acceleration, right, is the rate at which the velocity direction changes, right, as the object moves in a circular path. So we're looking at that first. So when we understand that, we can do the derivation. Alrighty? So firstly, right, everybody has these concepts covered. Alright? So from there we can move on. We're gonna have to use a little bit of, interesting movement in order to get everything together. Right? But let's have a look at this. So let's start with the acceleration here. We're trying to get the centripetal acceleration from these values and prove it. Centripetal acceleration is going to be equal to the change in the velocity over time, right? So we know that that is acceleration. Acceleration is going to be that, right? We can also reduce the acceleration, right? So if that is true, acceleration is also equal to this, right? So the change in the linear velocity as we stated here. So just breaking it down. So this is the same as that above, right? So this is the same thing as that. So V is equal, remember V is equal to R omega, all right? So we just plug that in right there, right? Since R is going to be constant, so I can just write since R is constant, because we're just looking at uniform motion, right? So R is going to be remain constant. A is going to be equal to R d omega over dt. Alrighty? But remember that the angular velocity is constant in uniform circular motion as well. So the derivative with respect to time doesn't change, right? Therefore, the magnitude of the centripetal acceleration comes from the change in direction and not the change in speed, right? So we're just looking at this. A is going to be reduced to R omega squared. So that's all we're looking at. Alrighty, any questions here? And if anybody wants to ask how did R become omega squared, how did we get that? What we're getting it from is a regular um acceleration, right? Linear acceleration, right? Which ends up being v squared over r, right? So if we were to look at the centripetal acceleration, that would literally just be r omega squared, right, over r, and then it can be reduced to a being equal to omega. No, that would be r squared. Let me just not skip any steps. Omega squared over r. So we end up with A equals R omega squared, right? So just in case anybody wants to ask, like, how is that possible, right? I'm just deriving them and putting them on the slide for you guys, all right? So that is how we got that, alrighty? So we derive it. So that is how we get that. So how is this in relation to that? How is the acceleration this and how is the acceleration that? We just derived all of them a while ago, okay? So we can move on to centripetal force. Or are there any questions before we move on to centripetal force?
You can move on.
Alrighty. So moving on. Da, 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 da. So that's what we're looking at there. So that would be centripetal acceleration, right? So we can move on to centripetal force. So as we stated earlier, the centripetal force specifically, it kind of speaks to really the force that is applied towards the center of the circular path, right? So if an object is moving, let me use a different color. If an object is moving, right, in a direction with velocity v, linear velocity v, right, there will be a force acting towards the center, right? And remember that the acceleration comes from that force component. So the acceleration is acting within the circle or towards the center of the circle, right? And when things accelerate, that means a force is being applied. That force is a centripetal force. So remember now, right? That's what we're looking at. So if we can recall from Newton's second law, right? So let's get this done. That is not Newton. That's not how I spell it, right? So from Newton's second law, what's Newton's second law again? Anyone? Just the equation.
Force equal mass times acceleration.
The force is equal to ma. Lovely, right? Mass times the acceleration, right? So from the equations that we've done above, right? Acceleration is equal to r omega squared, right? So r omega squared. Alrighty. So this is for the centripetal force, right? This is when we're using the angular velocity. So using angular velocity, right? So we know that the angular velocity is omega. So using angular velocity, we have that, right? But alternatively, right, we could have F is equal to mv squared over r, all over r rather, right? And this is when we're using linear velocity. All right, so we have that there. And remember now, so let's talk about this, right? This is force in newtons. This is mass in kilograms. This is the radius, right? Radius is what measured in what? Meters. And this is omega, right, in radians. So the angular velocity. Well, the angular displacement rather. Right, that would be in radians there. Alright? And then down here would be the same thing. So this force is in newtons, mass is in kilograms. This would be what? Meters per second, right? And then because it's squared, it's going to be squared. We have it squared. And then here we have the R, which is in meters. Alright? So everybody's okay with that derivation of the centripetal force. Because force is equal to ma, therefore, that's how we get that.
Yes, sir.
Alright. So let's get these equations down, right? So let's just recap everything. The key equations, right? So for angular displacement, what's the equation? Anyone? What is the equation for angular displacement? Remember, I can't see the chat, so I'm relying on you guys to like speak to me. So
Sir,
R
the change in speed
acceleration of the
over
time.
R.
repeat.
The change in speed over R.
The change in speed is the displacement. No, no, no.
Hmm?
All right, so we're gonna look at it. Right, so remember our angular displacement, right? Theta is going to be equal to our arc length over the radius, right? So this is the arc length over radius, all right? And this is measured in what?
Okay,
What's the
I was
unit?
mixing it up.
Okay, it's probably the S, mix it as speed, right? But,
Yes, it's the S.
and what are the units? Radians, right? It is in radians, rads. Right? What is the equation for angular velocity?
Change in omega over time.
All right, so we say omega. Right, so we're saying the angular velocity is omega is equal to what? Repeat.
Uh, the change in angular displacement over time. Or I change in omega over time.
There's not omega over time, right? Remember that omega is angular velocity, so it's going to be equal to the displacement over time, right? Displacement in radians over time. So this is going to be the angular
Oh,
displacement
oh,
over time. Okay. Remember, this can be written as delta that over delta t. So yeah, the relationship between the linear and angular velocity, right? That's just v is equal to r omega. What would be the equation for centripetal acceleration? That would be a. is equal to r omega squared, or it can be equal to v squared over r. And then the force, centripetal force, is going to be equal to m r omega squared, and well, or it is equal to mv squared over r. So those are the key equations that we have there, the key equations that we need. Alrighty. So yes, it is math, right? But hopefully, right, this will be simple, simpler after you review it. Okay. So are there any questions or concerns at this moment?